Welcome to the third topic, second lesson about gases and their properties. I'm Mr. Rast, and today we're going to talk about the ideal gas law. The ideal gas law is often referred to as PV-nRT, which is PV equals nRT. So far, we have talked about what P equals, that's pressure, and volume, that's V. And we've also talked about temperature, which should always be in Kelvin when we talked about the laws of Boyle's law, Charles' law, and Gay-Lussac's law. We used these three values. So we're introducing two new things right now. What is N and what is R? So what are they? P is pressure, and they can be represented in atmospheres, kilopascals, or millimeters of mercury for this class. With the millimeters of mercury can also, or is also, torr. So millimeters of mercury is also torr. And we talked about that. It doesn't look very good drawing with my mouse. But millimeters of mercury is also torr. We talked about that in the last lesson, what torr was. But that's supposed to be an R. So if you see millimeters of mercury, they're the same thing. So at standard conditions, 1 atmosphere is standard conditions. So 1 atmosphere equals 101 point, I'm talking about its standard conditions, 101.325 kilopascals, and which is also equal to 760 torr at standard conditions, which is also millimeters of mercury. Either way. Okay, that's a O, torr. Looks like an A. It's supposed to be an O though, okay, torr. All right, anyways, so it's standard conditions. This is something I need you to know for this test. And you can go back to topic 3, lesson 1 to review that. All right, so the new concepts that we're talking about here is, one, we're talking about moles. We're talking about moles, what's N. And this is just a number used for counting, but I'm going to get into that a little bit more in a moment. And the next thing is the ideal gas constant, R. R is going to be a constant that's going to be used basically to help you get from pressure, volume, the amount of a gas, and temperature, how they can relate back and forth there to each other. There's a constant, and the constant you do not need to remember, but you just have to know which one to use. And also remember, temperature is always in Kelvin. Don't use Celsius. That's a mistake that a lot of people make. Little mistakes, they get the whole question wrong if you use Celsius in your calculations. So R, remember, this is your R constant right here. It's different values for R. I like atmospheres. Most of my questions are in atmospheres. I see most questions written in atmospheres. That doesn't go without saying, though, that sometimes questions are given to you in kilopascals, the pressure's in kilopascals, or sometimes they're given to you in torr, which is also millimeters of mercury. The nice thing about having these three constants is if the pressure is in something that you are not comfortable with, if it's in atmospheres, you can just use this R constant. You don't have to change it into something else. So if you, for instance, if the question is giving you something and the pressure is measured in kilopascals, you just use this constant. You don't have to turn your kilopascals into atmospheres so that you can use this one. You may, and you'll get the same answer, but I will give you all three of these constants on a test. You don't need to memorize these constants. How do you know which one to choose? I'll reiterate. If you have your pressure in atmospheres, use this value. If you have your pressure in kilopascals, use this one. And if you have it in torr or millimeters of mercury, use this as your constant. So these are your choices to use. The next thing is on there was N. What and N I said was a mole. So what is a mole? A mole is a base unit for the amount of a substance. It's just a number we use to count things. Like if you go to a donut shop and you get a dozen donuts, we understand that that means 12. If I have 2 dozen students in my class, it's understood that I have 24 students because I have 2 dozen, 2 times 12. So a mole is a number just like a dozen is a number. And it can be used to represent anything. We use it often to count atoms or molecules in chemistry because we're dealing with such a large amount. We can't take like water as H2O. We don't do a lab where we can say, okay, let me have 2 hydrogen atoms and 1 oxygen atom and I'll build 1 water molecule. We're dealing with large quantities of atoms. We can't look at little single ones. So when we deal with these large quantities, we simplify it. Like if you're talking about a lot of donuts, we might talk about like I've got 5 dozen donuts here. So I might say I've got 5 moles of chlorine gas or something like that. So it's just a number. So don't get too caught up on what it is or like stressed out that it's something different. Just think of it as a number, just like a dozen is a number. Although moles is a very, very large number. A mole is 6.022 times 10 to the 23rd of anything. So like 1 dozen is 12, 1 mole is 6.022 times 10 to the 23rd of anything. Most often it's going to be atoms or molecules or elements or something like that. So this here is written with 4 significant figures. Up here we have a nice little illustration. It's only written with 3 significant figures. You know, if you're doing a problem with more significant figures, you'd want to make sure you have more significant figures in your work here. So please use this one. 6.022 times 10 to the 23rd moles is what a mole is. So if we were to expand that, we'd move the decimal place over 23 times. So we'd move it over 1, 2, 3, and 20 more zeros. It's a lot of zeros. We'll talk about how moles were derived in our next lesson. We talk about the atomic theory and the periodic table. But as a chemist, this unit, mole, is something you're going to deal with quite often. It is a very, very common unit that we use in chemistry, maybe the most common unit. So welcome to the mole. This is your first introduction to it, and we will be using it quite a bit. So having explained all that, maybe you could take a look at this question, pause the video, and see if you can answer this. You know what the ideal gas law equation is, and I told you what the pieces are. See if you can solve this. See if you can rearrange and solve this question. So we'll go ahead and pause the video right now and give it a shot. If you don't know where to start, and a lot of times people say this, like I just look at this, it's a blank paper, I don't know where to start. Just pull out some information. You do know that 3 liters is volume. You know that 3 liters is volume. So write that out. What's 300 K? You know that 300 K at this point is a measure of temperature. That's 300 Kelvin. We also know that we have 1.5 atmospheres. So you shouldn't have just a blank paper. You should pull some things out because you do know something. If you feel like you didn't know anything, and hopefully you worked this through already. So let's check what you got. So we're going to write the information from the problem. Like I said, you do know some things, so you could write this out. You know that the volume is 3 liters. You know that temperature is 300 Kelvin. You know that pressure is 1.5 atmospheres. And if you've done that, you might have got stuck and you said, hey, I don't know what R is. And I've had students do this, they're putting this out, but at least they're trying and they're figuring out what it is that they're struggling with, where the problems are. If you don't try, if you say, I don't get anything, that's telling me that you didn't try anything. If you don't get anything about it, then you didn't try anything in the first place. Because quite frankly, you could and should be able to get to this point. And this here, if we go back to our values here, our constants, we know that R, our constant R, is one of these 3. Now, because the question is written in atmospheres, I'm choosing the R value that is in atmospheres. So I'm going to choose this value. And that's what I was talking about when I talked about the constants. So we use this one, and then we're going to solve for the amount of moles. That's our N. And our formula is PV equals nRT. So now you might feel overwhelmed. You look at this question, I don't know how to do it. I don't know where to start. If you write down the things you know and what you're solving for, and you go back to the equation that you know, you might realize something that looks a bit overwhelming at first is something very, very manageable. If you take a look here, it's like, oh, I've got my P, I've got my V, I'm solving for N. I know R because I'm talking about atmosphere, so I'm going to use that constant, and I don't have to remember this. It'll be in my notes. It'll be on the test. And my temperature here. All of a sudden, it's like, hey, you know what? With a little manipulation of this equation, I can solve this. I can actually do this. So I'm just rewriting here. Moving up here, I've got my ideal gas law constant up here. I have our values here. So step 3 is to plug these things in. But if I'm going to solve for n, I want to rearrange the equation. So what does n equal? To solve for what n equals, I would take the RT and cross multiply, bring it to the other side, but I have to cross multiply, so that would bring it down as a denominator when you cross multiply. So it would be PV over RT. PV over RT equals n. So that's how I derived this right here, by cross multiplying, bringing the RT down. So now I know what n equals. And maybe that's where you got stuck if you're having trouble. So, but by trying, that's where you learn where you have the problems and how to fix that up. You gotta try. You just gotta try, guys. So let's plug in some values here. So n equals pressure 1.5, volume 3 liters, over R. Put our R value here, our R constant here, and times T. So we have this all here. And remember here, this R constant has a denominator in the constant, and it's already a denominator. And in class, I mentioned this a lot. The denominator of a denominator, so this is a denominator, and it has a denominator, is the same as a numerator. So this here, moles Kelvin, this here could be written as a numerator up here, which kind of helps when we start canceling units out, because the atmospheres cancel out with each other and the liters cancel out with each other right here, and the Kelvin, because it's a denominator of the denominator, they cancel out right here. But it could also be written as the moles Kelvin on the bottom. But what's more important is this moles here would be down here. It's a numerator, so we know, because it's the denominator of a denominator, it's actually a numerator, that this here would be what we're solving for. Our answer will be in moles. And so when all the units cancel out, that's a very, very good indicator that you're going to get the question right. If they don't cancel out properly, you know something's wrong. You got to go and take a look at something and the setup's wrong. So 1.5 times 3 divided by 0.0821 divided by 300. You put that in your calculator. Every opportunity to practice with your calculator is a good opportunity, because a lot of people make mistakes on their tests because they're not familiar with their calculator. They're setting this up right, but they just don't use the calculator very much, and they make some mistakes. So run this in, and hopefully you got what I got, and that was 0.18 moles. 0.18 moles with proper sig figs. I've got 2 in this question, and I got 2 here. I've got 3 significant figures here because there's a decimal place. That means these trailing zeros count. And I've got 3 significant figures here because there's a decimal place. This trailing zero counts. But this one only has 2, so therefore I'm going to only answer in 2. Remember, leading zeros never count as far as significant figures are concerned. So that's how you do an ideal gas law problem. Our workshop for topic 3, workshop 2, has 3 questions in here. I want to warn you, make sure that you convert your Celsius into Kelvin. You cannot answer in Celsius. I mean, you can't use Celsius in that equation. You'll get an incorrect answer. And then what R value use? Well, in this one here, you're going to use an R value for atmospheres, just like in our practice problem. This is just like the practice problem, except you just have to convert Celsius into Kelvin. Remember, you add 273 to Celsius and it's in Kelvin. Over here, determine the Celsius temperature. So you're going to get an answer in Kelvin, and then you're going to have to subtract to get it into Celsius. You're going to have to subtract your answer 273 from that. And you can get this one here. This one you're going to use your R constant that deals with kilopascals. And the final one, You have atmospheres again. You're going to use your R constant that's in atmospheres. And remember to change your Celsius and Kelvin. And besides that, it looks pretty straightforward. Good luck, and we'll go over this in class. If you have any questions, please come see me. That's what I'm here for. Have a good one. Bye.